The goal of our project is to extrude a lead-free brass. The reason we're doing this is that currently the only way to get a lead-free brass hollow is to machine down a solid rod to a hollow rod, which results in about 70 to 80% weight loss, and that has to get sent back to the material supplier, so it's a lot of waste.
Direct extrusion is the process where a solid piece of material, also known as a billet, is heated up and then placed in an extrusion press before it is pushed through what's called a die. Inside the die is a chamber, so as the extrusion material, so in our case it was a lead-free brass, is pushed into our die, it fills up the cavity or the chamber inside the die before it is pushed out through a smaller hole, making it a hollow tube. One of the advantages of doing extrusion over the common process for machining brass tubes is that during the extrusion process, there is very minimal, if any, material waste. In this illustration of direct extrusion, you'll notice that at the back of the billet there's an applied force that is pushing it into the die cavity, where it fills it before being pushed out the other end, which is a small hole, as a hollow tube.
The lack of lead in our brass makes it difficult to extrude, which leads to a lot higher temperatures required for extrusion, which is why not a lot of testing has been done yet.
In order to perform our hollow brass extrusion here at Michigan Tech, we use this extrusion press here. This press is capable of applying 55 tons of pressure at its maximum load. So to begin our extrusion, what we have to do is heat up three things: the chamber, which is located here, the die, and the billet. In our extrusion, the brass was heated to 750 degrees Celsius. However, our die and the chamber are both limited in the fact that they're steel, so they can only be heated up to 450 degrees Celsius. So that's what those were all heated to. After everything's heated, the billet's then loaded in here, pressed into the chamber. Your die is loaded in the front and locked into place because there's an immense amount of pressure on this. So if it's not locked in, this will come flying out like a bullet. You don't want that. And then you start pressing. During our extrusion, we maxed out the press at 55 tons, but it did extrude very, very slowly, about a rate of 1 inch per minute. But we did get a successful extrusion. We got about 3 feet. After that, the billet cooled down enough that it wouldn't press through the die anymore, because even at the high temperatures we're operating at, 750 and 450 degrees Celsius, the billet still cools down after a while, even to 400 degrees, at which point it locks up enough that it won't extrude any further.
So as you can see, this is the hollow that we extruded. It went really well. So as something is extruded into a hollow, it welds back together, you can see there. And ours had 3 bridges, so we have 3 welds. Looking at the microstructure of the welds, we can see that each weld is very strong. And the dimensions of the rod itself are very consistent.
We'd recommend that the billet be heated to around 800 to 850 degrees Celsius, as well as having the die made out of a different material than H13 tool steel. Something like Inconel would work. It can withstand the high temperatures and pressures from the extrusion process, and it also means that it can be heated up higher than 450 degrees Celsius, which is what the H13 tool steel's max temperature is.